I know of a time-saving equation you should probably memorize. The topic is, as you know, electrochemistry, using electricity to make chemistry happen, to force a transfer of electrons. Um, if we know the time it takes and we know the number of electrons transferred during the redox reaction, we can pretty easily calculate the amount of mass or moles of the substance created. So here's a story problem of creating purified palladium. Palladium 0 is the oxidation state for pure palladium solid, from palladium ions out of solution by giving them 2 electrons. Here's the half reaction. N, in this case, little n, the number of moles of electrons transferred is 2. 2 electrons gained by the palladium 2 plus ion would create palladium solid. You can do this with a unit conversion, but I never do because I have this equation memorized. There's another unit that we don't often come across in chemistry, but in electrochemistry we do. It's called the amp, or the ampere, abbreviated with a capital A. The amp is the flow of 1 coulomb of charge in 1 second. And by the way, an amp is a lot of electricity. So I wouldn't do it this way, but you can. Oh, by the way, your time has to be in seconds, because if the amp is 1 coulomb per second, then I want the seconds to cancel. So change the minutes to seconds, the seconds to coulombs, and the coulombs, what the heck? Okay, let's look at this. Memorize this equation. Moles plated or moles generated during a electrolysis experiment is equal to the current in amps times the time in seconds divided by the number of electrons transferred in the half reaction and also divided by this funky cursive capital F called Faraday's constant. It's what makes everything work out. It'll be given to you, but it's 96,500 joules per mole volt. Moles of electrons and volts in the bottom as well. Let's see a couple of examples. So how would I use that equation to solve this problem? Instead of remembering all those conversions, it's actually easier to remember the equation. The current's 3.2 amps. The time was 1800 seconds. Is that 3.2 minutes? And whatever we got upstairs, up there above, in a slide above. 2 moles of electrons transferred, Faraday's constant, comes out to the number of moles of palladium. And I can simply change moles of palladium to grams of palladium. Here I showed the unit cancellation. Coulombs per second times seconds. Number of electrons. This is moles of electrons times coulombs. The coulombs cancel, the seconds cancel. I'm left with moles. Moles. 0.02, almost 0.03 moles. That's so much fun, and if that's the first time you've seen it, let's try it again. So you can use that for gases as well. If I'm creating a gas through electrolysis, 3.2 amps again, creating a volume of oxygen by electrolyzing, using electricity, electrolysis to break down water. Here's 2 water molecules creating 1 oxygen molecule, 4 hydrogen ions. This is a half reaction, isn't it? Because I see the electrons over here unbalanced by the gain of electrons. Water can lose electrons and gain electrons, so these 4 electrons probably are going into another water reduction, gaining electrons where it creates hydrogen gas, but that's the other half of the story. This half of the story is 3.2 amps. 30 minutes times 60 seconds per minute gives 1,800 seconds. 4 moles of electrons transferred this time. The little n is 4. And again, Faraday's constant stays the same. And that would give me a number of moles of oxygen. I could use PV equals nRT from the Gen Chem 1 chapter on gases, or I could just remember or look it up, or maybe it's given to me that 1 mole of any gas is 22.4 liters at standard temperature pressure, and for a gas that's 1 atmosphere pressure and 273 Kelvin. Interesting. Or you can work it out this way if you like unit conversions, which I don't suggest. We also use electrolysis often to purify metals and purify sludge, but if I was purifying copper metal, you can do it pretty easily from solution. Or here's a big room of purifying copper through electrolysis. And the resolution on that's pretty poor. But the story is I put an impure metal over here, copper that might not be pure. I use a big old honkin' battery, a direct current. Doesn't work with alternating current. Alternating current, it goes back and forth and back and forth and back and forth and confuses the setup. But if I just push electricity in one direction, in essence, I force pure. Oh yeah, okay. So on the right-hand side of this setup is called the sacrificial anode, where I have my impure copper. It's forced to lose an electron and become a copper ion. The copper ion floats around in the water and is in essence more or less driven toward this other electrode called the cathode, where the copper ion gains electrons from the battery and repurifies into copper solid. The point in doing this, you say, well, here I'm going to make the ion and I'm going to create the ion. Here I'm going to destroy the ion. In a way, the copper travels through solution from here to here, but the reason why we do it is that a lot of the impurities are left behind. They either settle to the bottom or stay attached to this anode, but the impurities are left behind, and that's a way to purify the metal. What mass of copper in grams can be electrolytically purified if I use 2.1 amps over a million seconds? Ooh, that's 1,000 million seconds. So 10 to the 6 seconds, how many minutes is that? I'd have to do a little calculation. Could be a couple of days, huh? I don't know. Anyway, 2.1 amps coulomb per second times a million seconds, 96,500. Ooh, I got sloppy with my units there, but I know this always works out. So it came out to 10.88 moles of copper and times the molar mass of copper. Change moles to grams. You know, Professor White, you probably don't know Professor White. He's currently the Dean of the College of Science. He's actually a world-renowned, multi-award-winning chemist and electrochemist. He wrote up these notes because he thought it was interesting how you can show how we get that equation from something called Faraday's law. Consider the electrode deposition of tin metal from a solution of tin 2 chloride. I think I'll show this as a demonstration. It's way cool. The crystals of tin that grow out of solution are amazing. Here I have a reduction, gaining electrons. Here I have an oxidation, losing electrons. Looks like at one of the electrodes I generate oxygen gas, 4 electrons transferred. Here at the other electrode I'm gaining 2 electrons. I suppose to make this one and this one match up, I'd have to multiply this thing by 2. Take it times 2, take it times 2, take it times 2. But do you remember with electrolysis, you do not multiply this times 2. Very interesting. Sorry about this picture, it kind of got split between 2 pages, I apologize. So cut it with a pair of scissors right here, and slide this baby up and scotch tape it right there, and you got the setup with the tin. Oh man, that's unfortunate. What's happening is the tin 2 plus is gaining electrons from this side of the battery and becoming tin metal. So here in the tin aqueous is floating around in the water in the aqueous, and it is attracted to here and gains electrons to purify itself. Over here the water is losing electrons, becoming oxygen gas and 4 hydrogen ions in the water. What's the relationship between the electrical current that's like coulombs per second, amps? And so it's kind of strange for us chemists to think about things happening over time, but actually we did it when we talked about how fast chemical reactions happen. Here's a reminder of the definition of current, coulombs per second measured in amps. But Faraday's law says the charge is equal to the number of electrons transferred in the redox reaction times Faraday's constant times the number of moles of reacting species. Interestingly, the number of electrons transferred has no units. It's just 1 or 2 or 3 electrons transferred. What we can do is, if we are interested in how something changes over time, just do a little calculus. Say, how does the charge change with respect to time? But if I do it on this side, I got to do it on this side. So I could say, oh, wait a minute. The change in charge per time is called current. And the number of electrons transferred is constant. It's the same half reaction or overall reaction. And Faraday's constant comes out as well. But the number of moles involved can change. And so what I do is I separate the variables. I put the dt over here and the d number of moles over here, which sounds kind of odd to do. And so don't show your calculus teacher this. He might laugh a little bit. But us chemists are kind of sloppy mathematically sometimes. So after we do that, we integrate and add up over the time from 0 to time t, and from no moles to n number of moles. And this is just d number of moles, so you anti-differentiate this, and that's t. That generates a t, and this generates a number of moles evaluated from 0 to n, and it's just n number of moles. So that's where that equation comes from that it asks you to memorize above. Number of moles plated or generated, current times time, number of electrons transferred in the half reaction, Faraday's constant. So in this half reaction, if I was considering, looks like he wrote 100 milliamps, more reasonable than an amp or even 100 amps. How many grams of tin are deposited? The time was 10 minutes, 60 seconds in a minute. 100 milliamps is called 0.1 amps or 0.1 coulombs per second. In that 10, 2 plus going to 10, we have 2 electrons transferred. And lo and behold, it's a small number of moles. But if I multiply by the molar mass of 10, it's again a small number, a small mass, but milliamps, not very much. Ta-da! Voila! Done. Thanks for watching. See you in class, guys.